I'm currently a postdoc in the National Center for Nuclear Research in Poland, where I'm mainly working on machine learning algorithms in service of data extraction and catalog creation. And I would like to thank the organizers very much for letting me talk on this wonderful event. Okay, so this is the outline of my talk. It will be a bit basic, so I apologize in advance. My outline is that first I will give you a very basic information about what are the sky surveys, what can we expect from them, and then I will move to telling you about the discoveries of new objects and how they were handled in the past. Then I will tell you how can we tackle this task in this new era of data avalanche. And then I will show you some examples and applications of such algorithms, which can help us in this task. And I will try to summarize. Okay, so sky surveys are in general designed to provide as large and as deep as possible statistical samples of celestial objects. They aim to provide us, the users, with the best spatial overview that is currently available, and to provide us with complete and homogeneous data sets, which later on are serving as the very basis, a very foundation of any subsequent scientific analysis about the abundant objects that were detected in the survey. However, an additional attractive role that Sky Survey offers us is that they may contain some rare or unusual objects, which just so happen to be caught in the field of view. Right now we are mapping the sky through multiple different wavelength regimes. This is now done almost in an automatic way. We have the ground-based facilities and space-bound instruments which are doing that. And of course, the data reduction and data processing is also automatized. We have all sorts of pipelines. So basically, astronomers, as myself, we are on the top of the food chain as survey users because we are presented with a final product, which is an image, which is a catalog of sources, or a spectrum. So sky surveys come in different flavors. We have the difference, for example, in the way the data is acquired. We can have a photometric survey, we can have a spectroscopic survey. They also differ in the area that the survey is targeting. We have the deep surveys, which observe a very small patch of the sky, but by trade-off, they can reach quite deep into the space. We have wide surveys, which cover a little bit bigger areas of the sky, but it's the sacrifice that they have to make is that they cannot reach as deep as the deep surveys. And of course, we have the all-sky surveys, which are quite shallow, but we observe a large patch of the sky. And also, sky surveys are different due to the angle of the observed area with the respect from the observer. So by that I mean either we can observe we can observe the sky perpendicular to the galaxy plane, or we can observe the sky through the galactic plane. So the photometric sky surveys allow us to access a lot of information about the physics that is governing a target that we are trying to study. This is an example of the beautiful Andromeda galaxy observed through basically the full electromagnetic spectrum. We have radio waves which trace the H2 emission in the galaxy. We have the infrared observations which tell us about the new star-forming regions when young hot stars are being formed in the cocoons of dust. Their very highly energetic radiation is absorbed by the dust particles, and then those dust particles are re-emitting the radiation at longer wavelengths. So by that we are tracing the hidden star formation in the galaxy. Then we have the optical wavelengths, where we see the unobscured stellar populations, and X-rays, where we can trace the hot dust in the galaxy. So all that information combined can give us quite a good idea about different processes that are happening in the galaxy. This is an example of the whole spectral energy distribution of an emerging galaxy example, NGCU 7714. It's been observed through all possible wavelengths. We have the UV data from GALEX data, from GALEX satellite. We have the ground-based data from Subaru in the optical. We have the infrared data obtained by Akari, which traces the old stellar populations and the hot dust contained in the galaxy. And we have the Herschel observations of the far infrared tracing the peak of the cold dust emission. So when we have all this data combined, we can start to fit some templates in order to derive some basic physical parameters of such objects. For example, we can find out what is the star formation rate of the given object. We can find out what is the mass of dust contained in the galaxy. We can find out what is the extinction, what is the metallicity of the populations of stars that the galaxy has formed. So this is a very useful tool. And usually the photometric surveys are pointed blindly in the previously uncharted areas of the sky, simply by exposing different filters consecutively through a short wavelength range can give us already a rough idea about what kind of objects our survey can contain. So later we can infer what they are by looking at their spectral energy distributions. Then we have the spectroscopic surveys. They are, of course, measuring the electromagnetic spectrum of the object. However, they do need an input from the photometric surveys, simply because we need to know where the objects are and if they are really what we want to observe. Of course, sky surveys, both spectroscopic and photometric, can be done repeatedly if we are looking for some time variations. So in the terms of angle dependence of the sky survey, when we are pointing our telescope off the galactic plane, we should rather expect to see some extragalactic objects like AGNs, like galaxies, or some cool phenomena like mergers or gravitational lensing. And the lower we put our telescope towards the galactic plane, we should observe a larger variety of galactic objects in different stellar evolution stages, beginning from the young stars, young stellar objects, through the supernovae or asymptotic giant branch stars or planetary nebula, and the star-forming regions. So, of course, then we have the all-sky surveys, and I think one of the most successful so far is the Sloan Digital Sky Survey, SDSS. SDSS has observed, up to date, I think, the data release 14, it has observed 4 million objects spectroscopically, which cover almost 25% of the sky. And this is what I mean when I say it's most successful, because SDSS balances very well the trade-off between how deep we can observe the universe and how large the angle of the observation is. Of course, such observations are extremely expensive, both in time and money. So currently, the largest and the deepest sky survey available to the public is the all-sky survey performed by Wide Field Infrared Survey Explorer, WISE in short. It's an all-sky survey performed in the infrared wavelengths, covering the range from 3.6 to 22 micrometers. And WISE has detected over 700 million sources, which amounts to around 15 petabytes of data in total, including catalogs and images. So it's quite huge. The drawbacks of the survey are two general drawbacks of the survey. We have a very low angular resolution of the telescope. The beam is around 6 arcseconds, which means that in the very crowded areas of this galaxy, of the survey, we are going to expect a lot of blending. And the second one is that there was no spectrograph on board of WISE. So that means that we do not have any redshift information about the objects that are observed, and by default, we don't really know what WISE has observed. And right now, of course, we are entering this era of big data, or the future facilities are going to bring even more data than are currently available. The Zwicky Transient Facility will bring around 1 petabyte of data, which will amount to around 1 billion of objects. LSST is going to bring around 30 terabytes of data per night. And the Planck Square Kilometer Array is going to bring for over 4 zettabytes of data. And I had to Google what is zeta, and it's actually 10 to the 21st power, because it's huge. So in the anticipation of these new facilities and the data that they are going to bring us, people over 20 years ago started to ask questions like, how will this qualitative change in the data acquisition will change the way we do astronomy? Will we start to ask new kinds of questions about the universe, and will we find new ways to answer them? And most of all, how are we going to exploit this huge data avalanche in a systematic and effective way so that we can extract the essence useful for our science? So during this workshop, it's already very clear that all the areas of astronomy are being hugely advanced. All the daily routines of astronomers, like tracing the large-scale structure of the universe or the galactic of the Milky Way structure, has been brought to a much higher level of accuracy and detail. So this is very lovely, but for me personally, the most interesting aspect is that with this huge amount of new data, we will be finally able to explore the poorly known areas of the observable parameter space, where we can start to expect to find some rare types of objects or phenomena which we didn't expect to, or we didn't know about before. So speaking about the parameter space, we already have a large amount of parameters which we can exploit. We have the usual colors or fluxes of objects. We have the different wavelength regimes where objects are being observed. We have polarization, we have variability, we have morphology, you name it. So whatever we need for our science, it's already there. However, even though we are already measuring a lot of information about the universe, we still sample very limited volumes of the parameter space we are observing. Some axes, of course, are better constrained than others. We already have a great sky coverage in visible wavelengths, in infrared wavelengths, in radio wavelengths. However, we are still missing some pieces of the puzzle, like in submillimeter. And all these parameters are different in terms of technical limitations, like limiting surface brightness or the depth of the survey. So for example, some issues with the parameters that we have observed. For example, the morphological information is only of limited use for classification and when you are building catalogs. We have small-sized objects which, let's say, appear as extended in our survey. They don't necessarily need to be galaxies. They could be low luminosity quasars or simply projections of one or more objects onto the plane. And on the other hand, we have the compact objects, which not necessarily have to be stars or quasars, but they could also present an interesting class of compact galaxies. So the best example, I think, is on this Hubble picture. This is a picture of a quasar and a star next to each other. And just by using the compactness of the source, we cannot really tell them apart. But of course, we have ways to mitigate such problems. We can simply use other parameters. Like, for example, stars and quasars, if we measure the flux coming from these objects, they will appear as two separate groups, easily distinguishable, simply due to the different physics that govern the processes. So when we are looking for some particular objects, which are hard to find or they are relatively rare, we can always use some of the known properties or expected properties of them, like typical SEDs or their variability, to make them stand out from the common majority of objects. This is how historically different classes of objects were found. We have quasars, which were discovered as simply stars which have excess radio emission. Of course, now we know that the radio loud quasars are comprising only 13% of all known quasars, but that's a totally different story. Then we have, there was the discovery of the variable stars, which just show the particular shape of their light curves, and the discovery of ultraluminous infrared galaxies by IRAS satellite, which were found as anomalous objects which exhibited a very large far infrared to visible flux ratios. So sometimes when we find something rare or new, a simple wavelength cross-match between the observations can reveal some new and interesting aspect of otherwise regular object. When we are trying to target something new, we have to either invent a new combination of parameters or to find a new way to look at the data. Usually, the same methodology as searching for rare objects can be applied simply by finding an outliers in the suitable parameter space. And this is called an organized serendipity, which usually leads to some new discoveries. This is the simplest way. As an example, in early 2000s, the two teams, SDSS and DPOS, has joined forces in the quest of searching high redshift quasars. And they were targeting them by selecting an area of a color-color diagram where the known examples of high redshift quasars were appearing. And then, after selecting such targets, they were targeting them spectroscopically. And this is an example of an object that they found. It is a very peculiar spectrum, which at that point was completely unknown. Right now, we know that this is a low ionization, broad absorption line quasar, which is very rich in iron, which is located not that far, because at redshift 1.2. So that discovery means that even the areas of the parameter space which we think we understand can hide some very peculiar objects or some classes of objects which we previously didn't know exist. This is just another example of such a quasar, such a low ionization broad absorption line quasar, just located at a higher redshift, at 2.4. So right now we have a very nice new way of looking at the data, which is offered by machine learning. We can teach the computer how to recognize certain patterns in the abundant data. Then it will develop a model and make some predictions. We have three general branches of machine learning. We have the supervised learning, where we have to teach the machine how to recognize certain patterns. We have unsupervised learning, where the machine will find similarities between the data points without any bias coming from the user. And we have the reinforcement learning, where the machine is supposed to learn how to react to its environment. So, for example, we have a chess game, and we want the black pawns to win, and the machine has to tell us the best way for that outcome to happen, right? So the supervised learning is a great tool to search for some known objects with predictable signatures. This is perfectly suited for some simple tasks like star and galaxy separation, And it already has been done in many papers for many different wavelength regimes. However, it is very important to have the training set which is representative of the whole set of data that we have. So that is usually not the case. We are sampling usually very narrow area of the parameter space, and by default, with this approach, we are going to miss all the stuff that is new or unusual or interesting in this sense. So for that reason, photometric surveys like WISE, they still remain unexplored. So when searching for some anomalies in the data, unsupervised learning seems like a much more natural choice. Here, when we have a certain feature space with certain objects, we can cluster them, for example, into several statistically distinct classes, which will be modeled by whatever you want, by multivariate Gaussian clouds. And then we hope that these classes will correspond to some physical properties or to physical classes of objects like stars, galaxies, and quasars, or different types of galaxies. So by all means, this is a superior those are the superior algorithms to supervised learning from the theoretical point of view. However, this approach is extremely trial and error based, because each time we run the algorithm, we have to check whether those similarities the algorithm found have physical meaning that we can understand. So in total, this is really time consuming. So now I want to give you a few examples of the applications of detecting new objects from the literature. First, I will focus on my own research and my evolution and struggles. So once upon a time, my team in Poland tried to classify the WISE data into 3 general groups of stars, galaxies, and quasars. Since it's an unexplored survey, we thought that it would be a good idea to start with supervised learning. And to create the training sample, we positionally cross-matched WISE data with SDSS, simply because SDSS offers the widest area of the sky that is observed, while providing labels for our objects. As a parameter space, of course, we chose only the infrared data that was offered by WISE. And the algorithm of our choice was the support vector machines algorithm, which basically takes the input data from the input parameter space, maps it into a higher dimensional feature space, where it searches for an optimal separation hyperplane with as large margin as possible between the examples of the 2 or more classes that we are trying to find. And then the new data is assigned based on the relative position to that boundary. So we had a training set, we chose the parameter space, and we trained the algorithm, and this is the outcome. Here I want you to take a look at this distribution of the infrared color from 3.4 and 4.6 fluxes of WISE. The field histograms represent the training sample distribution, and the opened histograms represent the output distribution of the output sources classified as galaxies and quasars. And while you can see that the galaxy distribution seems to match, more or less, something went horribly wrong for the quasars. And coincidentally, this peak of the distribution for quasars, around 0.5 or 6, corresponds to the area of the theoretical color diagrams for WISE sources, where many different types of objects are overlapping. So what went wrong, basically, in this research is that we assumed that our matching of optical and infrared surveys will contain all the objects that should be expected in the survey. So to fix that, we have turned to anomaly detection algorithms. And specifically, we chose to use the semi-supervised learning, which is a happy marriage between the supervised and unsupervised approaches to handle the data, because not only we can build on what we know on our labeled data, but also the distribution of the unknown sources will give us very important information. So building on what we know, we can discover what we are missing in our training set. So we took a step back and applied the one-class support vector machines algorithm, which is a variation of the classical SVM algorithm. But here, instead of taking 3 distinct classes of training objects, all you have to do is to create one known class, which is filled with the labeled objects. And then the SVM maps those objects into a higher dimensional feature space, where instead of finding a hyperplane, it will find a decision boundary which will contain all the known objects. And then when you apply your new data that you want to classify, everything that falls outside of this decision boundary will be flagged as something that was unseen during the training, something new. So this is the result that we got. We found over 650,000 anomalies in the Ys, and they, when we plot their color diagram, they separate nicely into several groups. So since we got excited that we are maybe looking at something new or previously unknown, we wanted to check what is their nature. And unfortunately, like, majority of those objects turned out to be artifacts, which were unaccounted for during the pre-cleaning of the data. This was our first clue was the distribution of those objects over the sky. They were almost exclusively appearing in the galactic plane, where WISE is known to have problems with the blending. And upon checking, cross-matching this catalog with a different, but also infrared survey specifically targeting the galactic plane done by Spitzer, we found Spitzer has a much higher angular resolution. So we found that while we have a nicely looking singular object in WISE, in reality, it's a blend from 2 very narrowly separated but distinct objects. And together, in the large beam of WISE, they create a weird object with unphysical colors. So if anything else, the anomaly detection algorithms can help us to account for the previously unknown artifacts in the data, and they can also help to check whether the pipeline is working fine. So this is not a sad result, I think. The other group of objects turned out to be much more interesting. If you will ignore the galactic plane, their distribution seems quite uniform over the sky. And those 2 objects were chosen as anomalous because they experience an extremely sharp jump in the observed flux with the increase of the observed wavelength. So such an emission cannot be of stellar nature. It must come either from warm dust or from polycyclic aromatic hydrocarbon emission lines, which are characteristic for star-forming galaxies. And what is even more curious, almost 75% of those objects are undetected at other wavelengths, may be visible, radio, or ultraviolet. So we have applied for time to observe those objects, to characterize a bit their nature. And we have found many different types of objects. For example, we have found very high latitude young stellar objects, which really shouldn't be appearing that high above the galaxy plane. This is the spectrum. Forgive me the form, this is very new. So while the spectrum looks like it could really be the young stellar object, the shapes of the emission lines are weird. So by talking to experts, they told me that it could be because of the rotation of the object. However, I still need to do some more work about it, but definitely this object is not common. Later, we found a bunch of mergers. if you will take a look at this low-resolution DSS image, we can see that it looks normal. In WISE, it gets this kick in the flux at longer wavelengths. And when we took a picture with the acquisition camera, it turned out that they are two objects merging together. And from the spectroscopy, we found that actually this is a galaxy. There are two galaxies undergoing a merger. And finally, we have found red type 1 quasars. Type 1 quasars are the objects which we observe kind of face on. We observe the nuclear regions face on, in contrast to type 2 objects, which we observe, where we observe the nuclear region through the disk of material accreting onto the black hole. And while the spectrum looks usual, it looks like a normal quasar, their infrared properties indicate that the host of the galaxy, contains some larger scale structures of dust. So to give you another example, not to just talk about my own work, there is a lovely paper about titled The Weirdest SDSS Galaxies by Byron, published in 2017, where they took an unsupervised approach to anomaly detection within the SDSS spectroscopic data. They used the unsupervised random forest, and their database is huge because they have over 2 million objects, which are described by over 15,000 features. The features are the flux at each wavelength. They have, they have defined the weirdness parameter, and all the outlying objects that they found turned out to be indeed of special interest. I don't know if you can see, but they found a bunch of, not only a bunch of bad spectra and blends in the data of SDSS, but also they have found objects with extreme O3 widths of the emission line, or objects with very weird line ratios. Some objects that I find are the most interesting among all these are, for example, this very strong Balmer line galaxy. This strong absorption indicates that this object has recently experienced a shift in its star formation activity. There are no indications of an ongoing star formation. There are no O and B stars. However, there are still some less hot stars like A stars, which are still on the main sequence of their life in the galaxy. And there are indications of an existence of an AGN in this galaxy, which is inferred from the very large width of the H-alpha emission. So this object could actually represent a very special stage of galaxy evolution, where the galaxy underwent a recent merger, and the activity of the AGN has truncated the star formation. However, there is still a lot of material left for the black hole to feed. So such objects are very rare, and they could contribute a lot to the field of galaxy evolution and coevolution of AGNs and their host galaxies. Another group that they have found are the objects with weird emission line ratios. When you plot them on the BPT diagram, it turns out that certain objects, which are classified when using one type of emission line ratios, they are classified as, for example, star-forming galaxies. But when you use a different set of emission line ratios, they appear on a different part of this diagram. So they are classified, for example, as AGNs. So these objects are very curious. There's not so many of them. However, their algorithm pinpoints very well such weirdness in the objects. So now I would like to just summarize what I've been talking about. I think that the searching for rare and unexpected phenomena is a must now when we are going to get all the data from the new generation facilities. And searching for such new objects is becoming more and more realistic. with the help of anomaly detection algorithms. Last time I checked, there was over 10,000 of objects, algorithms designed specifically for that task. If you are interested, you can take a look at some nice reviews. There is many more, but I found those two particularly useful. And the reason why I was showing you my evolution, which led me to using the anomaly detection, is that if you're working on similar problems like catalog creation for your analysis, you don't have to make the same mistakes as I did, because I already did them. So, all right, so that's it. Thank you.